The NVIDIA Certified Professional Generative AI LLMs Certification represents the pinnacle of LLM engineering validation. This is not an entry-level certification. It's designed for senior engineers who design, optimize, and deploy production-grade large language models at scale.
In this comprehensive guide, we'll cover everything you need to know about NCP-GENL, what it validates, the 10 technical domains with detailed breakdowns, a week-by-week study path, prerequisites, hands-on project requirements, exam strategies, and preparation resources. By the end, you'll have a complete roadmap to certification success.
NCP-GENL. The NVIDIA Certified Professional Generative AI LLMs validates your ability to design, train, fine-tune, and deploy production-grade large language models. Unlike entry-level certifications that focus on using LLMs, NCP-GENL specifically targets engineers who can design and train custom LLMs from scratch, implement advanced optimization techniques like quantization, pruning, and distillation, deploy distributed training across multi-GPU clusters, optimize inference performance with TensorRT-LLM, build production RAG pipelines that scale, fine-tune models using PEFT, LoRA, and QLoRA, profile and benchmark model performance, and deploy models using NVIDIA NIM and Triton Inference servers.
The target audience includes senior ML engineers, LLM specialists, AI solutions architects, and deep learning engineers with 2 to 3 years of production LLM experience. This is critical. If you haven't worked with production LLMs, trained models larger than 7B parameters, or deployed distributed training systems, you'll find this exam extremely challenging. The exam expects you to have battle-tested experience optimizing models in real production environments, not just theoretical knowledge.
Let's cover the exam format. The exam consists of 60 to 70 questions, takes 120 minutes, and costs $200 USD. It's delivered online through Certiverse with remote proctoring. The certification is valid for 2 years from issuance. NVIDIA doesn't publicly disclose the passing score, but based on professional-level difficulty, you should aim for 75 to 78% on practice exams to ensure you pass with confidence.
Professional educator. The exam covers 10 technical domains. Understanding the weight distribution is crucial for effective study planning. The 2 largest domains are model optimization at 17% and GPU acceleration at 14%. Together, these represent 31% of your exam score, nearly 1/3 of the entire exam. This tells you exactly where to focus your preparation efforts. Let's explore each domain in detail, starting with the heavyweight domains.
Professional educator, Domain 1, Model Optimization at 17%. This is the largest domain and the most critical for passing. It covers production deployment strategies, containerization and orchestration, TensorRT-LLM optimization, quantization techniques including INT8, FP16, and INT4, pruning and distillation, accuracy versus latency trade-offs, memory optimization, and inference acceleration. This domain is where theoretical knowledge meets production reality.
TensorRT-LLM is NVIDIA's flagship inference optimization framework, and you need deep hands-on experience with it. For INT8 quantization, TensorRT-LLM supports weight-only quantization, which quantizes model weights to 8 bits, while using FP16 or BF16 for activations. Smooth quant is a key technique that applies pre-processing to model weights. For batch sizes less than or equal to 4, weight-only quantization is preferred due to memory bandwidth constraints. For batch sizes 16 or greater, FP8 quantization is prioritized because it offers the best balance of performance and accuracy.
Quantization scaling modes in TensorRT-LLM include per-tensor scaling using a single factor for all elements, per-token scaling with different factors per token, and per-channel scaling. Best practices recommend per-tensor quantization for activations and per-channel quantization for weights, as this empirically leads to the best quantization accuracy. FP8 KV cache quantization is recommended over INT8 on Hopper and Auto GPUs because it has lower accuracy impact. Switching from FP16 to FP8 KV cache enables 2 to 3x larger batch sizes on H100, bringing approximately 1.5x performance benefits.
Performance expectations. INT8 Smooth Quant delivers 1.40 to 1.45x speedup for Llama 3 models, with up to 1.81x for larger models. When optimizing a 70B parameter model from 200 milliseconds to 50 milliseconds latency while maintaining 95% accuracy, you need to understand the trade-offs between quantization level, calibration methods, batch size optimization, and KV cache quantization. This is the type of practical scenario the exam heavily tests.
Professional educator. Key skills for model optimization include optimizing models with TensorRT-LLM, implementing quantization strategies, balancing accuracy and performance, deploying containerized models with NVIDIA NIM, profiling and benchmarking inference, and reducing model size and latency. Example questions might ask, what quantization level provides optimal trade-off for a 70B parameter model serving 1,000 requests per second? How do you implement dynamic quantization with TensorRT-LLM while maintaining 95% accuracy? And what container orchestration strategy ensures 99.9% uptime for production LLM inference? Domain 2, GPU acceleration at 14%. This is the second largest domain and covers the backbone of modern LLM training. It includes multi-GPU setups and parallelism, distributed training strategies including data parallelism, model parallelism, tensor parallelism, and pipeline parallelism, performance profiling with Nsight systems, tensor core utilization, memory optimization and gradient checkpointing, DGX system configuration, CUDA optimization, and communication optimization with NCCL. 3D parallelism is the foundation of large-scale LLM training. DeepSpeed and Megatron-LM created an efficient 3D parallel system combining data, pipeline, and tensor slicing parallelism. Tensor parallelism from Megatron-LM distributes tensor shards across GPUs for parallel processing, scaling the model within a node using high-bandwidth NVLink. Pipeline parallelism from DeepSpeed vertically splits the model across GPUs at the layer level, enabling 2 to 7x faster training on clusters with limited network bandwidth. Data parallelism with Zero removes memory redundancies by partitioning optimizers' state, gradients, and parameters across data parallel processes, reducing memory consumption by 8x compared to standard data parallelism. Choosing the right parallelism strategy depends on model size and hardware. For a 530 billion parameter model, the optimal configuration uses 8-way tensor slicing within a node and 35-way pipeline parallelism across nodes, spanning 280 NVIDIA A100 GPUs. Tensor parallelism requires significant communication between GPUs, limiting compute efficiency beyond a single node. Pipeline parallelism reduces communication volume, making it ideal for multi-node training. 0.2 is 10 times faster than Megatron-LM alone and 5 times faster than 0.1 for models of the same size. Understanding NVIDIA GPU capabilities is essential. You need to know tensor core utilization for mixed position training, memory bandwidth constraints for different generations of GPUs, NVLink for high-speed GPU-to-GPU communication within nodes, and DGX system architecture with optimized networking and storage.
You must understand when to use tensor cores, how to optimize memory with gradient checkpointing, and NCCL communication patterns for efficient multi-GPU and multi-node training.
Professional educator GPU acceleration skills include configuring multi-GPU training, implementing parallelism strategies, profiling GPU performance with N-site systems, optimizing memory usage with gradient checkpointing and mixed precision, leveraging tensor cores for accelerated computation, and designing DGX workflows. Example questions. Which parallelism strategy is optimal for training a 175B parameter model on 64 GPUs? How do you diagnose and fix GPU memory bottlenecks during training? What NCCL configuration minimizes communication overhead in multi-node training? How do you configure 3D parallelism for a model that doesn't fit on a single GPU? Professional educator. Domain 3. Prompt engineering at 13%. This domain covers chain-of-thought prompting, zero-shot and few-shot learning, domain adaptation techniques, prompt optimization strategies, in-context learning, instruction tuning, prompt templates, and meta-prompting. While prompt engineering might seem simple, the exam tests deep understanding of when and why different techniques work.
Chain-of-thought prompting is particularly effective for mathematical reasoning tasks because it forces the model to show its work step by step, reducing errors. Few-shot learning requires careful selection of examples that are representative, diverse, and ordered correctly. In-context learning performance depends on example quality, relevance, and the model's ability to identify patterns. Instruction tuning adapts base models to follow instructions more reliably. Meta-prompting involves prompts that guide the model to generate better prompts.
Professional educator. Prompt engineering skills include designing effective prompts for different tasks, optimizing prompt performance through iteration, implementing few-shot learning with strategic example selection, adapting prompts to specific domains, measuring prompt quality with metrics and human evaluation, and engineering instruction formats. Example questions. When should you use chain-of-thought prompting versus direct instruction for mathematical reasoning tasks? How do you optimize few-shot examples to maximize in-context learning performance? What prompt engineering technique reduces hallucination in knowledge-grounded question answering? How many examples are optimal for few-shot learning in different contexts?
Professional educator. Domain 4. Fine-tuning at 13%. This domain covers full fine-tuning approaches, parameter-efficient fine-tuning, or PEFT, LoRA and QLoRA techniques, adapter methods, custom data preparation, model customization for specific use cases, instruction tuning, RLHF basics, and catastrophic forgetting prevention. The key is understanding when to use each technique based on computational constraints and performance requirements.
Professional educator. LoRA, or low-rank adaptation, inserts trainable low-rank decomposition matrices into transformer layers while keeping the base model frozen. This dramatically reduces the number of trainable parameters, often by 10,000x or more. QLoRA extends LoRA with quantization, loading the base model in 4-bit precision to further reduce memory requirements, enabling fine-tuning of large models on consumer GPUs. LoRA rank and alpha are critical hyperparameters. Higher rank increases expressiveness, but also parameters and computation, while alpha controls the scaling of LoRA updates.
Choosing between full fine-tuning, LoRA, and QLoRA depends on your constraints. Full fine-tuning updates all parameters, achieving maximum performance, but requiring massive GPU memory and compute. LoRA is ideal when you have limited GPU memory, but still want strong performance, reducing memory by 3x and training time significantly. QLoRA is best when GPU memory is severely constrained, enabling fine-tuning of 65B models
on a single 48-gigabyte GPU. For domain adaptation with limited data, LoRA or QLoRA is preferred to prevent catastrophic forgetting of the base model's capability.
Fine-tuning skills include implementing full fine-tuning with proper learning rate schedules, applying PEFT techniques like LoRA and adapters, configuring LoRA rank and alpha hyperparameters, preparing high-quality training data with proper formatting, preventing catastrophic forgetting through regularization and data mixing, and evaluating fine-tuned models. Example questions. When should you use LoRA versus QLoRA versus full fine-tuning for domain adaptation? How do you configure LoRA rank and alpha to balance efficiency and performance? What data preparation strategies prevent catastrophic forgetting during fine-tuning? How much training data is required for effective instruction tuning?
Professional educator. Domain 5. Data preparation at 9%. This covers dataset curation and cleaning, tokenization strategies, vocabulary management, data augmentation, quality filtering, bias detection, data mixing ratios, and pre-processing pipelines. Data quality is often the difference between a mediocre model and an excellent one. Skills include curating high-quality datasets from diverse sources, implementing tokenization with proper handling of special tokens and rare words, managing vocabularies to balance size and coverage, filtering low-quality data through heuristics and learned classifiers, detecting and mitigating bias in training data, and designing efficient data pipelines that can process billions of tokens.
Professional educator. Tokenization strategy significantly impacts model performance. For multilingual LLMs, sentence piece or a carefully designed BPE tokenizer with balanced vocabulary across languages is optimal. Vocabulary size involves trade-offs. Larger vocabularies reduce sequence length, but increase embedding parameters, while smaller vocabularies increase sequence length, but reduce rare word issues. Data mixing ratios balance general capability and domain expertise, typically 80 to 90% general data and 10 to 20% domain-specific data, though this varies by use case. Professional educator. Domain 6, model deployment, at 9%. This domain covers inference pipelines, real-time monitoring, batch versus streaming inference, API design for LLM services, load balancing, auto-scaling, model serving patterns, and canary deployments. You'll need to design inference pipelines that efficiently process requests, implement comprehensive monitoring with latency, throughput, error rate, and quality metrics, build robust LLM APIs with proper error handling and rate limiting, configure load balancing across multiple model replicas, enable auto-scaling based on traffic patterns, and deploy safely with canary deployments that gradually roll out new model versions.
Professional educator. Inference serving patterns most match your traffic profile. Batch inference optimizes throughput for offline workloads by processing multiple requests together. Streaming inference minimizes latency for real-time applications by returning tokens as they're generated. Hybrid approaches buffer requests briefly to increase batch size while maintaining acceptable latency. For variable traffic LLM APIs, hybrid serving with auto-scaling based on queue depth and P99 latency is optimal. Triton Inference Server provides the foundation with support for TensorRT-LLM, dynamic batching, and concurrent model execution. Domain 7, evaluation at 7%. This includes benchmarking methodologies, error analysis techniques, evaluation metrics like perplexity, BLEU, Rouge, and BERT score, human evaluation frameworks, A/B testing for LLMs, regression testing, and domain-specific metrics. Skills include designing comprehensive evaluation frameworks, implementing standardized benchmarks, performing detailed error analysis, conducting rigorous A/B tests, running human evaluation studies, and creating custom metrics for specific use cases. Perplexity measures how well the model predicts the next token. BLEU and Rouge evaluate text generation quality. BERT score uses embeddings for semantic similarity.
Professional educator.
Evaluation strategy depends on your application. Instruction following capability requires human evaluation or LLM as judge with carefully designed rubrics, as automated metrics often miss nuanced instruction adherence. A/B testing for comparing fine-tuned model variants requires careful experiment design with proper randomization, sufficient sample size, and multiple metrics, including task performance, latency, and user satisfaction. Human evaluation is required when automated metrics don't capture quality dimensions like helpfulness, harmfulness, or factual accuracy, while automated metrics suffice for well-defined tasks like translation or summarization where reference outputs exist.
Professional educator. Domain 8, production reliability at 7%. This covers monitoring dashboards, uptime maintenance, logging and observability, incident response, performance degradation detection, failover strategies, SLA management, and cost optimization. You need to build comprehensive monitoring systems tracking latency percentiles, throughput, error rates, model quality metrics, and resource utilization. Maintain high uptime through redundancy, health checks, and circuit breakers. Implement observability with distributed tracing, structured logging, and metrics aggregation. Respond to incidents with clear runbooks, escalation paths, and post-mortem processes. Detect degradation through anomaly detection on quality metrics. Optimize costs by right-sizing infrastructure, using spot instances, and optimizing batch sizes. Professional educator detecting subtle LLM quality degradation requires monitoring semantic similarity of outputs, toxicity scores, factual accuracy rates, and user feedback metrics, not just latency and throughput. Automatic failover for LLM inference services uses health checks with multiple replicas, load balancer failover to healthy instances, and circuit breakers to prevent cascade failures. Cost optimization strategies that reduce inference costs by 40% or more without quality loss include using quantized models with TensorRT-LLM, optimizing batch sizes, using spot instances with fallback to on-demand, caching frequent requests, and right-sizing GPU types based on throughput requirements. Professional educator. Domain 9, LLM Architecture at 6%. This domain covers transformer architectures, attention mechanisms, including multi-head attention, multi-query attention, and grouped query attention, positional encodings like absolute, relative, rope, and alibi, model scaling laws, architecture trade-offs, mixture of experts, and sparse architectures. You need to understand transformer internals, including self-attention, feed-forward networks, layer normalization, and residual connections. Compare attention variants. Multi-head attention uses separate query, key, and value projections for each head. Multi-query attention shares key and value across heads, reducing memory and computation. Grouped query attention groups heads to share keys and values, balancing efficiency and expressiveness.
Positional encodings enable transformers to understand sequence order. Absolute positional encodings are added to input embeddings. Relative positional encodings, like rope, encode relative positions in the attention mechanism, improving extrapolation to longer contexts than seen during training. Alibi adds a constant bias to attention scores based on distance, also improving length extrapolation. Model scaling laws describe how performance improves with model size, data size, and compute. Chinchilla scaling laws suggest compute optimal training uses equal scaling of model parameters and training tokens. Mixture of experts architectures use sparse activation of expert subnetworks, increasing model capacity with modest compute increases.
Exam strategy. Domain weights guide your study focus. Prioritize model optimization at 17% and GPU acceleration at 14%. Together, they're 31% of the exam. Master TensorRT-LLM quantization techniques. Understand scaling modes and performance trade-offs. Learn 3D parallelism with DeepSpeed and Megatron-LM. And practice configuring distributed training. Then focus on prompt engineering and fine-tuning at 13% each, mastering LoRA, QLoRA, and PEFT techniques. Don't neglect smaller domains like production reliability and safety. They're easier points to secure and can make the difference between passing and failing.
Professional Educator, Domain 10, Safety and Ethics at 5%. This covers bias detection and mitigation, responsible AI practices, content filtering, hallucination prevention, privacy considerations, safety benchmarks, red teaming, and guardrails implementation. Skills include detecting and mitigating bias through data audits, debiasing techniques and fairness metrics, implementing content filters that balance safety and utility with classifiers and rule-based systems, preventing hallucinations through grounding, attribution, and confidence estimation, protecting privacy with data minimization and differential privacy, conducting safety testing through adversarial probing, and deploying guardrails with input-output filtering and safety layers. Detecting and mitigating gender bias in LLM outputs requires measuring bias in word embeddings and generated text, using metrics like bias scores and stereotype detection, mitigation through counterfactual data augmentation, and careful curation of training data. Content filtering that balances safety and utility uses multi-tiered classifiers with escalating restrictions, contextual understanding to avoid overblocking, and human review for edge cases. Red teaming methodology for uncovering LLM safety vulnerabilities includes adversarial prompt design, automated jailbreak attempts, diverse testing scenarios, and systematic documentation of failure modes.
Now let's cover the recommended 8 to 10-week study path. This is an intensive preparation program designed to build both theoretical knowledge and hands-on skills. The study path is structured to build progressively, starting with foundations and moving to advanced optimization and production topics.
Professional Educator. Week 1. LLM Architecture Foundations. Review transformer architecture in depth, including self-attention mechanisms, multi-head attention, feed-forward networks, layer normalization, and residual connections. Study model scaling laws, including the chinchilla optimal training approach that balances model size and training tokens. Learn attention mechanism variants, multi-head attention, multi-query attention, which shares keys and values across heads, and grouped query attention, which balances efficiency and expressiveness. Study positional encodings, including ROPE and alibi. Take Practice Exam 1 untimed to establish your baseline and identify knowledge gaps.
Weeks 2 and 3. Prompt engineering and fine-tuning. Master prompt engineering techniques, including chain-of-thought prompting for reasoning tasks, few-shot learning with strategic example selection, zero-shot learning for generalization, and instruction tuning for reliable instruction following. Study fine-tuning techniques. Full fine-tuning, which updates all parameters, PEFT or parameter efficient fine-tuning, LoRA, which uses low-rank decomposition matrices, and QLoRA, which combines LoRA with 4-Beck quantization. Review Hugging Face PEFT library documentation and examples. Hands-on project. Fine-tune a 7B model using LoRA for a domain-specific task, experimenting with different rank and alpha values. Take Practice Exam 2 untimed, targeting 60% or higher.
Weeks 4 and 5. GPU acceleration and distributed training. Study parallelism strategies in depth. Data parallelism, which replicates the model parallelism, which splits layers across GPUs, tensor parallelism, which splits individual tensors, and pipeline parallelism, which processes different microbatches in different stages. Learn the 3D parallelism approach, combining all three. Study distributed training frameworks, DeepSpeed with zero optimizer state partitioning, and Megatron-LM with tensor parallelism. Understand DGX system configuration with NVLink for intranode communication and InfiniBand for internode communication. Study NCCL optimization for efficient all-reduce operations. Hands-on project. Implement multi-GPU training with DeepSpeed or Megatron-LM on a model that doesn't fit on a single GPU. practice and cite systems profiling for GPU performance optimization, identifying bottlenecks in computation and communication. Take Practice Exam 3, timed, aiming for 65% or higher.
Weeks 6 and 7, Model Optimization and TensorRT-LLM. This is critical and the most heavily weighted domain. Deep dive into TensorRT-LLM optimization techniques. Master quantization. INT 8-weight-only quantization for small batches. Smooth quant for activation quantization. FP8 quantization for large batches with best performance accuracy trade-off, and INT4 for extreme compression. Understand calibration methods, scaling modes including per tensor, per token, and per channel. Study accuracy latency trade-offs empirically. Learn KV cache quantization. FP8 is preferred over INT8 on Hopper and Ada GPUs. Study pruning, which removes less important weights, distillation, which transfers knowledge from large to small models, and containerization with NVIDIA NIM for production deployment. Hands-on project. Optimize a model with TensorRT-LLM, measure latency improvements, and plot the accuracy-latency Pareto frontier for different quantization configurations. Take Practice Exam 4, timed, targeting 70% or higher.
Week 8, Production Deployment and Monitoring. Study production deployment patterns with Triton Inference Server, including dynamic batching, concurrent model execution, and model ensembles. Learn monitoring and observability, metrics for latency percentiles, throughput, error rates, and model quality, distributed tracing for request flows, and structured logging. Study incident response with runbooks, escalation procedures, and postmortems. Master load balancing across multiple replicas, auto-scaling based on queue depth and latency targets, and SLA management with defined uptime and latency guarantees. Understand canary deployments that gradually shift traffic to new model versions. Hands-on project. Deploy a production LLM API with Triton Inference Server. Implement comprehensive monitoring with Prometheus and Grafana, and test auto-scaling behavior. Take Practice Exam 5, timed, aiming for 73% or higher. Week 9, Data Preparation, Evaluation, and Safety. Study data preparation, including dataset curation from diverse sources, tokenization strategies for multilingual models using sentence piece or BPE, vocabulary management balancing size and coverage, quality filtering using heuristics and learned classifiers, bias detection in training data, data mixing ratios, typically 80 to 90% general and 10 to 20% domain-specific, and efficient pre-processing pipelines. Learn evaluation methodologies, Perplexity for language modeling, BLE and Rouge for text generation, BERT score for semantic similarity, human evaluation frameworks, and A/B testing with proper experimental design. Master safety practices, bias detection and mitigation through data audits and debiasing, content filtering with multi-tier classifiers, hallucination prevention through grounding and attribution, privacy protection with data minimization, safety benchmarks, and red teaming with adversarial prompts. Review responsible AI frameworks. Take Practice Exam 6, timed, targeting 75% or higher. Week 10, Final Review and Exam Readiness. Retake practice exams 4 through 6 until you're consistently scoring 78% or higher on each. Focus intensive review on model optimization at 17%. Ensure you can explain TensorRT-LLM quantization techniques and trade-offs, and GPU acceleration at 14%. Be confident with 3D parallelism configurations. Review weak domains identified in practice analytics with targeted study. Speed practice. Complete 70 questions in 110 minutes to leave a 10-minute buffer, simulating exam pressure.
Final review of official NVIDIA documentation for TensorRT-LLM, Triton Inference Server, and NeMo framework. Create quick reference notes for quantization levels, parallelism strategies, and key metrics. Only schedule your exam after achieving 3 consecutive practice scores of 78% or higher. This ensures you have sufficient margin above the likely 65 to 70% passing threshold.
Here's a critical insight that many candidates miss. Studying LLM theory without hands-on optimization experience is insufficient. The exam heavily tests practical scenarios that require real experience. For example, your 70B model has 200 millisecond latency serving at 100 requests per second. You need to reduce latency to 50 milliseconds while maintaining 95% accuracy and supporting 500 requests per second. What combination of quantization method, batch size, KV cache optimization, and serving strategy achieves this? Answering this requires actual experience optimizing models with TensorRT-LLM, measuring performance, and understanding real-world trade-offs. Theory alone will not suffice. You need to have actually profiled models, experimented with quantization, and seen the performance impact firsthand.
Let's discuss prerequisites and recommended experience. This exam requires substantial real-world experience that cannot be obtained through courses alone.
Professional educator experience. Required. 2 to 3 years in AI or ML roles with production LLM experience, meaning you've deployed models serving real users. Hands-on distributed training on multi-GPU systems with at least 4 GPUs, experiencing the challenges of parallelism and communication overhead. Experience optimizing models for inference, reducing latency while maintaining quality. Production deployment experience, including monitoring, incident response, and scaling. If you lack any of these, build that experience through personal projects or work assignments before attempting the exam. The exam will expose gaps in practical experience.
Professional educator. Technical skills required. Advanced Python programming, including decorators, context managers, and asynchronous programming. C++ basics for optimization work and understanding CUDA kernels conceptually. Deep understanding of PyTorch, including AutoGrad, distributed training, and custom operators, or equivalent TensorFlow expertise. Multi-GPU and distributed computing knowledge, including collective communication primitives. Containerization with Docker for model packaging and Kubernetes for orchestration. Linux system administration, including process management, resource monitoring, and network configuration. Git for version control and MLOps practices, including experiment tracking, model versioning, and CI/CD pipelines.
Professional educator LLM knowledge required. Transformer architecture internals, including the mathematical formulation of the tension, why it works, and its computational complexity. Distributed training techniques and when to apply each. Model optimization, including quantization theory, pruning strategies in knowledge distillation. Fine-tuning methodologies, including PEFT, LoRA mathematics, and QLoRA implementation. Production deployment patterns, including batching strategies, caching, and load balancing. Performance profiling and benchmarking, including identifying bottlenecks and optimization opportunities. This is deep technical knowledge, not surface-level familiarity.
The gap between associate and professional is substantial. NCP-GENL is significantly more advanced than NCA-GENL. While associate covers LLM fundamentals like what transformers are, basic prompting, and simple fine-tuning, professional tests production engineering, configuring distributed training on 64-plus GPUs with optimal parallelism strategies, optimizing 70B+ models with TensorRT-LLM quantization, and measuring the performance accuracy frontier. Designing fault-tolerant inference systems with automatic failover and degradation handling. If you haven't trained models larger than 7B parameters on multiple GPUs, deployed production LLM APIs serving thousands of requests, or debugged distributed training failures, build that experience before attempting NCP-GENL. The difficulty jump is similar to the difference between knowing how to drive a car and being able to tune a race car engine.
Professional educator. Essential hands-on projects you must complete before the exam. Project 1. Fine-tune a 7B plus model like Llama 2 or Mistral using LoRA for a domain-specific task. Experiment with rank values from 8 to 64 and alpha values. Measure performance impact. Project 2. Implement multi-GPU distributed training on 4 or more GPUs using DeepSpeed or Megatron-LM. Train a model that doesn't fit on a single GPU, requiring model parallelism. Profile communication overhead with Nsight systems. Project 3. Optimize a model with TensorRT-LLM. Apply INT8, FP8, and weight-only quantization. Measure latency improvements and accuracy degradation. Plot the Pareto frontier. Project 4. Deploy a production LLM API with Triton Inference Server. Implement health checks, monitoring with Prometheus, alerting, and load testing. Test auto-scaling and failover behavior. These projects give you the battle-tested experience the exam assumes.
How does NCP-GENL compare to other certifications? NCA-GENL is the associate level, taking 60 minutes with entry-level difficulty. It focuses on LLM fundamentals, transformer basics, simple prompting, and basic fine-tuning. NCP-AAI, also professional level, focuses on agentic AI systems, including multi-agent orchestration, tool use, autonomous reasoning, and agent-based architectures, instead of LLM optimization. NCP-GENL is best for senior LLM engineers focused on training large models, optimizing inference performance, and deploying production systems. If you're focused on AI agents, autonomous systems, and agentic workflows, consider NCP-AAI instead. Many senior engineers pursue both NCP-GENL and NCP-AAI to cover the full spectrum of generative AI expertise. Registration process. First, create an account at certiverse.nvidia.com. Second, purchase the exam voucher for $200. Third, schedule your exam date and time, allowing a minimum of 4 to 6 weeks for preparation based on your current experience level. Fourth, prepare your exam environment, working webcam for proctoring, government-issued ID for identity verification, clean workspace free of notes and additional monitors. Fifth, take the exam online with a live proctor who will monitor via webcam.
Professional educator. Retake policy. Your first attempt is included in the $200 exam fee. If you fail the first attempt, there's a mandatory waiting period before the second attempt, not publicly disclosed by NVIDIA, but likely 14 to 30 days based on industry standards. Additional retakes cost $200 each with no limit on attempts. This makes failure expensive. Combined with potential $500 to $1,000 spent on NVIDIA initial courses, failing multiple times becomes costly. Invest in comprehensive practice exams to ensure you pass on the first attempt. The exam is criterion referenced, measuring absolute competency rather than ranking candidates, so there's no curve.
Professional educator exam preparation the week before. Retake flagged practice questions from all exams, focusing on questions you got wrong or guessed. Review TensorRT-LLM documentation, including quantization techniques and API usage. Review NeMo framework documentation for distributed training. Review Triton Inference Server documentation for deployment. Skim key research papers on techniques covered, LoRA, QLoRA, quantization methods, parallelism strategies. Test your computer, webcam, and internet connection with the Certiverse platform. Get consistent 7 to 8 hours of sleep. Cognitive performance degrades significantly with sleep deprivation.
Professional educator. Exam day tips. Have a light breakfast or lunch. Avoid heavy meals that cause post-meal drowsiness, which peaks 1 to 2 hours after eating.
Review quick reference notes for a maximum of 30 minutes, quantitation levels and their use cases, parallelism strategies and when to use each, key metric formulas like perplexity calculation. Use the restroom before starting. You can't pause during the exam. Log in 15 minutes early to resolve any technical issues. Stay calm and remember you have 120 minutes for 60 to 70 questions, which is approximately 1.7 to 2 minutes per question, more generous than most certifications.
During the exam, read questions carefully. Watch for qualifying words like not, except, best, most, and least, which change the question's meaning. For optimization questions, systematically consider trade-offs: latency impact, accuracy degradation, memory requirements, and cost implications. For GPU questions, think through parallelism strategy selection based on model size and cluster tautology, memory efficiency with gradient checkpointing and mixed precision, and communication overhead with NCCL collective operations. Flag uncertain questions for review and mark them to move on. Don't get stuck on one question. Use process of elimination on tough questions by removing obviously wrong answers to improve your odds. Review all flagged questions with remaining time, applying fresh perspective. Submit with a 5-minute buffer to avoid last-second technical issues.
Time management is critical for success. With 120 minutes for 60 to 70 questions, you have approximately 1.7 to 2 minutes per question on average. Complex optimization scenarios requiring analysis of multiple factors may need 3 to 4 minutes to work through all trade-offs and eliminate wrong answers. Straightforward recall questions take 30 to 60 seconds. Budget your time accordingly. Don't rush through questions to finish early. Accuracy matters far more than speed. Use extra time to review flagged questions and double-check calculations. If you're consistently finishing practice exams with significant time remaining, you're likely rushing and missing details.
Professional educator. How difficult is NCP-GENL compared to NCA-GENL? NCP-GENL is significantly more challenging. While NCA-GENL tests foundational LLM knowledge, like what attention is and basic prompting techniques, NCP-GENL tests production engineering skills, selecting distributed training strategies for 100B+ models, including whether to use tensor, pipeline, or data parallelism, and at what ratios. Quantization trade-offs with TensorRT-LLM, including choosing between int8 smooth quant, FP8, or weight only based on batch size and accuracy requirements. Multi-GPU profiling with N-Site systems to identify communication bottlenecks and optimize NCCL. And production deployment architecture, including load balancing, auto-scaling, and failover strategies. Expect scenario-based questions requiring deep technical knowledge and real-world experience. Without 2 to 3 years of production LLM work, passing is extremely difficult. The passing rate is likely significantly lower than the associate exam.
Do you need to know NVIDIA hardware in depth? You need to understand NVIDIA GPU capabilities at a systems level. This includes tensor cores and when they're utilized during mixed precision training, memory bandwidth constraints of different GPU generations, and how they impact quantization benefits. NVLink for high bandwidth GPU to GPU communication within a node with 600 gigabytes per second bandwidth. And DGX system configurations with optimized networking using InfiniBand for multi-node communication. Focus on how to configure multi-GPU training with proper topology awareness, when to use tensor cores versus CUDA cores, memory optimization strategies, including gradient checkpointing and activation recomputation, and NCCL communication patterns for efficient all-reduce, all-gather, and reduce-scatter operations. The exam tests using NVIDIA hardware effectively,
not designing hardware or writing CUDA kernels.
Can you pass without multi-GPU distributed training experience? It's very difficult and unlikely. GPU acceleration is 14% of the exam as an explicit domain, and distributed training questions appear throughout model optimization, fine-tuning, and other domains, making the effective coverage closer to 25%. You need hands-on experience with data parallelism using distributed data parallel, model parallelism, splitting layers across GPUs, tensor parallelism, splitting individual tensors, pipeline parallelism, processing different microbatches and stages, and tools like DeepSpeed with zero optimizer state partitioning, or Megatron-LM with efficient tensor parallelism. If you lack this access to a multi-GPU system, cloud providers like AWS, GCP, and Azure offer A100 and H100 clusters that can be rented by the hour. Train models larger than 7B parameters that require multiple GPUs before attempting the exam. The practical questions will expose any lack of hands-on experience.
How much does TensorRT-LLM knowledge matter? It's critical and non-negotiable. Model optimization is 17% of the exam, the largest domain, and TensorRT-LLM is NVIDIA's flagship inference optimization framework tested extensively. You must know quantization techniques in depth. INT8 weight only for small batch scenarios, INT8 smooth quant for weight and activation quantization, FP8 for large batch scenarios with best performance accuracy, and INT4 for extreme compression. Understand when to use each based on batch size, accuracy requirements, and hardware. Know calibration methods, including min-max and entropy calibration. Understand accuracy-latency trade-offs empirically, not just theoretically. Know how to measure performance improvements, including latency, throughput, and memory usage. Without hands-on TensorRT-LLM experience, optimizing at least one model and measuring results, you will struggle significantly with this domain and likely fail the exam.
How long does the certification remain valid? 2 years from the date of issuance. To maintain certification, you must retake the exam before expiration. LLM technology evolves rapidly with new architectures like Mamba and RWKV, new optimization methods like GPTQ and AWQ, and new deployment patterns emerging regularly. NVIDIA updates the exam content annually to reflect the latest techniques, tools, and best practices. Recertification every 2 years ensures your skills stay current with industry standards and that your certification remains valuable to employers. Treat recertification as an opportunity to learn new techniques rather than a burden.
Professional educator. What programming languages do you need to know? Python is essential and non-negotiable. 90% of LLM work is done in Python, including training, fine-tuning, and deployment. You need advanced Python proficiency, including object-oriented programming, functional programming, decorators, context managers, and asynchronous programming with async I/O. C++ knowledge is valuable for understanding optimization work and CUDA kernel concepts, but you won't write C++ or CUDA code on the exam. Focus on PyTorch proficiency, including autograd mechanics, distributed training APIs, custom operators, and performance optimization. Understand distributed training frameworks like DeepSpeed and Megatron-LM at a conceptual level with some hands-on usage. Familiarity with CUDA concepts like thread blocks, grids, shared memory, and memory hierarchy helps understand GPU performance, but you don't need to write CUDA kernels. Containerization with Docker for packaging models and dependencies is essential. After you pass, what's next? First, claim your digital badge. Check email for Credly badge notification within 2 to 3 business days after receiving results. Add the badge to LinkedIn by clicking Add to Profile and to your resume in the certification section. Second, update LinkedIn comprehensively. Add to certification section with completion date. Update your headline to include your certification, such as Senior LLM Engineer, NCP-GENL Certified,
And share an achievement post describing your preparation journey and what you learned to inspire your network. Leverage your certification strategically. Filter job searches for LLM Engineer, ML Optimization Engineer, AI Infrastructure Engineer, and Deep Learning Engineer roles. Highlight your certification prominently in applications, ideally in the Summary section and Certifications section. Discuss your certification and practical experience in interviews using it as evidence of expertise. Negotiate compensation confidently, as certified professionals with proven optimization skills command premium salaries. Continue learning. Stay current with NVIDIA's AI blog for latest techniques and tools. Follow research on Megatron-LM updates, TensorRT-LLM improvements, and new optimization methods. Contribute to open-source LLM projects to maintain practical skills and build your portfolio. Consider advanced specialization. Pursue NCP-AIA for agentic AI expertise. Cloud certifications on AWS, Azure, or GCP machine learning platforms, or specialized NVIDIA courses on emerging techniques like mixture of experts or sparse architectures. The importance of practice exams cannot be overstated. Preparing for NCP-GENL requires hands-on practice with realistic, scenario-based exam questions. Reading documentation and watching videos builds foundational knowledge, but practice exams teach you how to apply that knowledge under time pressure, identify your weak domains for targeted study, get comfortable with the question format and difficulty level, and build confidence and reduce test anxiety. You need exposure to questions that test optimization trade-offs, like choosing between quantization methods based on batch size, distributed training decisions like configuring 3D parallelism ratios, and production architecture choices like designing auto-scaling policies. Preporato offers the most comprehensive NCP-GENL practice exam platform purpose-built for this certification. Let me walk you through exactly what's included and why it's effective. What's included in Preporato: 7 full-length practice exams with 420 to 490 total questions, providing extensive coverage of all 10 domains. Detailed explanations for every single answer, not just correct answers, with direct links to official NVIDIA documentation so you can dive deeper. Performance analytics dashboard tracking your scores across all 10 domains with visual charts to identify weak areas requiring additional study. 120-minute timed mode with a realistic question interface that matches the actual exam format, helping you practice time management. Scenario-based questions testing real optimization trade-offs like reducing latency while maintaining accuracy. Distributed training decisions like choosing parallelism strategies for specific model sizes and cluster topologies. And production architecture choices like designing failover and auto-scaling systems. Domain study guides with architecture diagrams explaining complex concepts like 3D parallelism visually, code examples demonstrating techniques like LoRA implementation, and best practices distilled from production experience.
Why choose Preporato? Questions are expert developed by NCP-GENL certified engineers with real production LLM experience, optimizing models, deploying distributed training, and running production inference systems. Content reflects the latest 2025 exam blueprint and NVIDIA platform updates including TensorRT-LLM 0.15 and Triton 2.48. Heavy emphasis on model optimization at 17% and GPU acceleration at 14%, matching the actual exam weight distribution. Questions test real-world scenarios like optimize this 70B model from 200 milliseconds to 50 milliseconds latency while maintaining 95% accuracy. What combination of quantization, batching, and caching works? Students score 15 to 20 percentage points higher after completing all practice exams, based on aggregated performance data. At $49 for all 7 exams versus a $200 retake fee, Preporato delivers 4x ROI if it helps you pass on the first attempt, not counting the time saved avoiding retakes.
Final thoughts on NCP-GENL preparation? This is a challenging but achievable certification for engineers with the right preparation and experience. Success requires a 3-pronged approach.
theoretical knowledge from NVIDIA documentation, official courses, and research papers, hands-on experience from real projects, training, optimizing, and deploying models, and strategic preparation focusing on high-weight domains and practicing with realistic questions. Don't attempt this exam without sufficient production experience. Build that experience first through work projects or personal projects. Focus your study time on model optimization and GPU acceleration, which together comprise 31% of the exam. Practice extensively with timed exams to build speed and confidence. Only schedule your exam after consistently scoring 78% or higher on practice tests.
Professional educator, ready to master production LLMs and earn your NCP-GENL Certification? Visit Preporato.com to access comprehensive practice exams, detailed study guides, and performance analytics that identify your weak areas. Our platform has helped hundreds of engineers pass on their first attempt. Start your certification journey today with a clear roadmap and proven preparation resources. Good luck with your preparation, and remember, the investment you make in thorough preparation pays dividends throughout your career as a senior LLM engineer.